Okay guys, this is the second video in our discrete structures series. Today we're going to be introducing propositions and the things we can do with them. So propositions are simply statements that can be made mathematically, or we'll see them in English first. So an example of a proposition would be "it is raining." It's anything that can be proven true or not true. And we represent these propositions with any letter variable. Typically you'll see P and Q as the ones that are most used. And then conjunction is simply the English or the mathematical representation of the word "and" in English. So if we have two propositions, P and Q, we can say P and Q, and that's how we'd write it. Similarly, we have disjunction, which is "or" in English, and this is how we represent it. It's just the opposite of "and." So P or Q would be that. So if we have two propositional statements that say "it is raining," and then the other one would be "I am home," so we can say P is "it is raining," Q is "I am home." So P and conjunction Q would be "it is raining and I am at home," whereas P disjunction Q would be "it is raining or I am at home." And then negation is this symbol, and it means not. So how we do this is we put this onto individual statement or propositions, or we can put it onto multiple compound statements. So we can say like not P. So if we go back to "it is raining," negation P would just be "it is not raining." And then we can put this also on bigger compound statements. So if we go back to our P and Q and we do this, we can negate that whole statement, and then this would distribute through. And when you do negations on compound expressions, you negate the sign too. So we would distribute the negation. Negation times negation is, well, negative times negative positive. So we'd have P, and then you flip this because the negation of conjunction is disjunction, and vice versa, and then negation Q. There we go. So that's what this is. And logical equivalence is represented with this. Mathematical equivalence is just that's the equal sign, but logical equivalence is 3 lines. Yeah, let's move on. Propositions, like I mentioned briefly, can be either true or false. There's no in between. They are true or they are false. Implication means that one proposition implies another. So for example, if I go back to our example of "it is raining and I am at home," if I say P implies Q, and P is "it is raining," Q is "I am at home," this would say if it is raining, then I am at home, because "it is raining" implies that I'm at home. It's basically creating a conditional statement. Truth tables are one way to prove logical equivalence and to derive different logical statements. So a truth table is basically a table of all the existing combinations of possibilities between true and false. So we take the number of propositions and do 2 to that number, and that's how many rows we're going to have, how many combinations. So just to exemplify this, we have proposition P and proposition Q, and this can be true or true false, and it can go the other way. So false true, false false. So as we see, we have two statements. 2 to the power of 2 is 4 rows. All right, and then negation P. So we go to the P column. It's true, so it turns to false. Same with the Q, false. And then negation of true, false. Negation of false, true. Okay, and now we can do P and Q. So this statement is true only when both of the operand statements are when both of the operand propositions are true. So P in this instance is true and Q is also true. so we would come over here and put true. I'll start using the mouse because I don't think you can really see the pen pointer. So P and Q, P is true, Q is false, so this is going to be false. And then you can do the rest: false, true, false, 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 false. This is based on the true condition, not the false. So this would be false and false. Alright, and then we have P or Q. As you can probably assume, it's going to be when one or the other is true. So true, 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 not true. So true, 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 and then none of them are true, so false. And that's what a truth table is. This is a way to prove logical equivalence, which we'll cover next video. Let's move on to implication. As I mentioned earlier, implication is where one proposition implies another. So we have the same two propositions, and there's two of them, so we have four possibilities. So P implies Q. This means we have to look at Q. So in this instance, Q is false and P is true. So true does not imply false. So this would be false. How you can think of this is whenever the rightmost, the one that's being applied, the proposition being implied, is true, then this implication is always going to be true. So if we look, this is true and this is true, so this always has to be true. And then the other condition that makes this statement true is when we have two falses. So a false implies a false. Since they're the same, this becomes true. That's a little tricky to get, but I'll go through this one more time. True, false gives you a false implication. True, true gives you a true implication. False, true gives you a true implication because the thing that's being implied is true regardless. And then false, false is true because this implies the same. It's a little confusing to think about, but you'll get it the more you do it. So we'll go the other way. Q implies P, so false implies true. That's true, so we'll put true since this is the thing being implied. This is true, true. This is true, so it's the implication is going to be true no matter what. And then Q is true, P is false, so this is going to be false since the thing being implied is false and the thing implying is the opposite. So false. And then same as the P implies Q, Q implies P, they're both false, so this will become true. Okay, moving on. We have some things that we can do to the statement. So here's our statement: Q implies P. This applies to implications. So we have three ways of manipulating this. We can take the converse, the contrapositive, or inverse. With the converse, we're simply flipping which is being implied. So Q implies P becomes P implies Q. And then the contrapositive is where we're flipping what becomes implied, and then we're negating both statements. So we have Q implies P turns to negation P implies negation Q. And then inverse is just flipping it to not flipping, rather we're just negating both statements. So Q implies P becomes negation Q implies negation P. Alright, we have a if and only if statement. So this happens only when both statements are true, or the same rather. When they're both the same, it doesn't have to be based on true. So here if we fill out this truth table, we have true, false, this would be false. We have true, true, that would be true. False, true is false, and then false, false, since they're the same, true. Alright, in the next video, we're going to go ahead and try to prove the equivalence of two compound statements. This basically means that we'll have some P's and Q's in a statement, and then we are going to have to prove that that equals another compound statement that has multiple P's and Q's in it. Alright, catch you later.